So welcome everyone. It's nice to launch off our 2025 OERC seminar series with an opportunity to hear from what I hope you all enjoyed and sort of your summer scholarship experience, the four of you that were involved with that. So this is something where OERC provides funding, and then the host department matches that, and it gives students an opportunity to do a wide range of energy-related work. So something fun to do over the summer. So we'll have an opportunity to hear from each of those four students, and there'll be some time for questions. All right, can I invite Francesca to come up in the first instance? Hear about your project.
Kia ora everyone, Francesca. And over summer, I had the opportunity to do a summer research project looking at data given to us by Aukaha of indoor air quality of like low-income Dunedin homes after they'd done some health labs. Okay, so a bit about me. I did energy management for 3 years, and now I'm doing an honours project looking at how climate change is going to impact wind energy in the future. And my project was supervised by Michael, Jack, and Helen Figures from So indoor air quality in New Zealand has had pretty limited research, especially compared to other similar countries. It's really important that we start understanding temperature and humidity and CO2 in houses because it's a really important part of our health. And on average, Kiwis spend over 50% of their time indoors. So, you know, understanding indoor air quality is really important. Aukaha's Otago Energy Retrofit program made improvements to homes in a lot of ways. They used warm Kiwi Homes grants to improve insulation, provide clean heating mechanisms, and did critical repairs such as fixing windows, or lots of windows were actually like painted and sealed shut, and so they had no way to just naturally ventilate houses. So kind of undoing any of that. The aim of my summer research project was to analyse the temperature, CO2 and humidity in over 130 Dunedin homes that have received home improvements to better understand the relationship between CO2, humidity, and temperature. The analysis looked at both some survey answers that we got and also the thermometer data. So first of all, looking at the surveys don't really fully represent everyone. It was only people who answered the surveys, and it's hard to sort of get funding for survey questions before a project. But before intervention, 97% of people said that their house was sometimes or more colder than they'd like in winter. 58% said their house was cold enough to see their breath in winter. 47% said that there was sometimes or more significant mold in their house, and that's pieces of like bigger than A4 pieces of paper, so pretty significant. And 70% said they experienced poor well-being due to their situation. But on the other hand of that, after the intervention, 81% agreed that their house felt better ventilated, 90% felt that their house felt drier, 84% agreed that their house felt less damp, and 54% agreed that they had improvement in mental health. And really importantly is that 86% said they made behavioural changes regarding heating in their house, which really highlights kind of just a lack of energy education, and it's a really simple fix. So, you know, it's a first step, and it's an easy one that we can make to provide a better energy education. So this was just a random sample taken from July 2023 for a week. And this is a kind of tells us a lot about what we saw through all of the data, which is that the indoor temperature, even after the Better Homes intervention, still the indoor temperature is not really reaching an ideal temperature for, the whole week. And same with humidity, it's way over the healthy range. We're looking at 80% humidity inside someone's house. CO2 was pretty good across most of the houses though, but older houses have a lot of that natural ventilation going on. So to kind of get an understanding of what was going on in all these houses, I plotted the average temperature versus the average humidity of each client through the month of July. So each dot represents a different house and takes their average July temperature and the average July humidity. And what we found was that, quite see it, but less than 25% sat within that healthy range, which was that green box up there. And 60% of the clients were outside of the healthy range for both temperature and humidity. And so that's their average across all of July in 2023. So we don't know what the data was like before. 25% could be a really great improvement. 25% more people in the healthy range, but there's still a lot of people outside. Oh yeah, so the next thing we saw was that even though July was really bad, the rest of the year was also pretty poor performing, especially for humidity. In fact, the summer months were even more humid, which is interesting because Dunedin feels pretty dry to most of us, but inside these houses, there's a lot of humidity going on. We've got to ask, where's this coming from? What else is going on? And same with the temperature for most of the months. It was below the healthy range for almost all of the clients. So what we've got here is the average for each client for each month, and this is the standard deviation. This is kind of just another demonstration for time outside of the healthy range, and this is for all of 2023. So some houses, a lot of houses, were spending almost 100% of their time outside of the healthy range for humidity and temperature. And so more than 100 clients spent more than 50% of their time outside of the healthy range. We also wanted to look at the relationship between humidity and temperature. And what we found is that the poor performing houses, so those were the ones kind of at the bottom of the scatter plot outside the healthy range, they didn't really show too much relationship between humidity and temperature. But the well-performing houses, so we use the Aukaha office, which is very well built building, showed a much stronger relationship. This kind of makes us wonder, where's all this external humidity coming from in these poor performing houses? We also looked at the outdoor temperature versus indoor temperature, and you can see that the well-performing house doesn't have any relationship whatsoever with the outdoor temperature. It's, it's well insulated. It's fact the temperature and humidity are more from internal controls, but the outdoor houses definitely experienced more of a correlation with the outdoor temperature. CO2 levels were mostly in the healthy range. There's a few outliers, but they kind of relate to just one or two buildings. And the CO2 is pretty healthy for everyone else. We just also compared the best and worst performing houses. So looking at their humidity and temperature. So the worst performing house is looking at, you know, in that 80% humidity range for a whole week, and you know, down at 10 degrees for a whole week as well. Whereas the best performing house was in that lower humidity range, much higher temperature range. So in summary, less than 25% of houses experienced an average temperature and humidity within the healthy range, and more than 60% of the houses did not meet either criteria. Most of the houses reflected healthy CO2 levels consistent with good ventilation, which poses the question, like, why so many houses so humid? Humidity levels performed most poorly in the summer and autumn months, with the standard deviation lying outside the healthy range from January to May, as well as November and December. The standard deviation for monthly averages of all clients sat outside the healthy range for temperature for June, July, August, and September. And houses within the healthy range showed a stronger relationship between temperature and humidity, whereas houses outside of this range tended to show. So that's all in terms of the kind of information we gathered. I also want to say a thank you to the Go Energy Research Centre for funding my summer project, and my supervisors, my project and also to Aukaha for providing us with this data. Yeah, does anyone have any questions?
Thanks, Francesca. That was really good. Any questions?
I was just wondering what the intervention actually was, the one that you mentioned at the beginning.
Yeah, so that intervention kind of varied for each house. So for some, like I said, was unsealing windows so that they can ventilate their house better. For some, it was they didn't have any sort of heating means in their house. You know, they just had a broken fire. So then getting some heat pumps in, and then adding a bit of like insulation where they could. Yeah, it was definitely a huge range, like leaky taps, leaky pipes in their house to try and get that humidity down. It was just whatever they could do. Like, yeah.
I have a question about the high humidity in the summer. Is that, how much of that is behavior of the people in the house, do you think? Or
Well,
I know you're speculating.
yeah, I
but
mean, I couldn't say.
Yeah.
I think this was, all of this information is from after they learned about what they can do and everything else. I think that you probably can't attribute a lot of that to just behavior. A lot of that could be, you know, you'd know as soon as you went in the house, and we couldn't really do that, but I'm guessing like leaky pipes could really cause a lot of humidity inside houses. I know a lot of Dunedin flats deal with that. Yeah, so we don't really know, but I think the people who were on site would have probably been able to gauge what was going on.
I'm just thinking, because you would assume that windows would be open.
Yeah, well, it did kind of discuss that lots of people didn't really know that, you know, you shouldn't dry your laundry inside, or like having an extractor fan above the oven. So there's definitely a lot of like basic education needed. And I'm sure it's not just these homes, you know, it's been
So was all the data after the intervention?
yeah, so they can really collect data before the intervention because, well, it costs a bit of money and they're a not for profit. And so even though they know how helpful it would be, it's just not really something that's on the card. So yeah, all the data's after the intervention.
But there's still obviously
Still a lot of work to be done. Yeah.
Great, thanks.
Great.
Really shows the importance of interventions and how more is needed.
Yeah. Thank you.
Great, thanks. All right, next up we have Charlie.
Hey guys, I'm Charlie. So my summer project was to prepare 2 manuscripts based on my honours work, which was on condensing plate heat exchangers. So HVAC, which is heating, ventilation and air conditioning, accounts for 20% of global electricity use and 8% greenhouse gas emissions. So heat exchangers are a very valuable component in these systems. So the efficiency of it is very important to increase the efficiency of the whole system. So we have various different types of heat exchangers. We have the thin tube heat exchanger that's predominantly used in various HVAC applications like heat pumps. We have the shell and tube that's used in more heavy industrial processes like power plants. We have the gasket heat exchanger, HVAC, which is heating, ventilation and air conditioning. It accounts for 20% of global electricity usage and 8% of greenhouse gas emissions. And these HVAC systems use heat exchangers. And there's many very different types of heat exchangers. We have the thin tube heat exchanger, which is used in heat pumps and air conditioning. We have microchannel that's used more in automotive applications. And we have shell and tube heat exchangers, which are used in more heavy processes like power plants and chemical manufacturing. Down here we have plate heat exchangers, the gasket one that's used mainly in like residential heating. So we use them to heat up the whole university pretty much because that's connected to the district hot water. So the focus, my work, is a flat plate heat exchanger. These can be put in dehumidifiers and cloth dryers to make them more efficient. And in these applications, condensation forms in them. But condensation is actually a big issue in these heat exchangers because it decreases the performance and decreases the performance of the whole system. So we want to remove as much condensation as possible. But luckily, nature's created the surfaces which increase the hydrophobicity. So these surfaces increase water shedding along the grain for the surface, but actually across the grain, water shedding is decreased. So people have figured out many ways to rectificate the surfaces, but the one of interest for this project is 3D printed surface. So when you 3D print something, a natural artifact is these little micro ribs, and these are similar to that of butterfly wings and rice leaves, and they also have similar water shedding properties. So the objectives for this then was to create plate heat exchanger from 3D printing that should, well, it does have these microlines embedded in it, and that should hopefully increase the rate of condensation removal and then increase the performance. We also developed a CFD model to predict the performance of an aluminum heat exchanger as well as the plastic heat exchanger, and that just allows us to validate our results. So the 2 manuscripts were prepared on this work. The first presents the model and the validated against the results for the aluminum heat exchanger, and the second manuscript presents the polymer heat exchanger and the effect of the microlines in the performance. So here's how the plastic one was made. It was 3D printed 20 segments that were all glued together. Each segment took about 20 hours. And then for the metal one, in a similar fashion, 18 plates were made with CNC manufacturing and glued together. Here's the rig that were tested in. As you can see, cold air, well, first of all, the plate heat exchanger is situated in here, and then cold air travels horizontally through here and is heated by this hot stream, which is cooled simultaneously. And it's cooled to the point where condensation occurs. And that condensation drips out and is measured by these digital scales here. They're both situated in psychrometric chambers in the basement, which can control the test conditions perfectly. It shows about 3 test conditions to test each heat exchanger on. So here's the results for the model and in the experimental results. The dashed lines are the model and the solid lines are the experimental results. On the left, we have the pressure drop here. So the hot side pressure drop is higher because the condensation blocks the airflow in the ducts. But the model did not predict this because it's very complex phenomena to simulate, so we didn't include that in simulation. Here you can see the temperature difference at 3 tested conditions for each heat exchanger. The hot side temperature difference is lower than the cold side because it's a phase change process, and that's what happens. You don't have as much of a temperature change during the process. But the model predicted that very well. You can see the lines line up very closely, but for the middle heat exchanger, not as well, because on the middle one, there's condensate on the outside, the top part of it, but that's not included in the simulation. And then the graphs at the end, that's the kilograms of condensation produced per hour, and the model is very close to that, so we get a tuning factor into the model. These are results for the 3D printed heat exchanger. Now this is pressure drop at the 3 tested conditions. Pressure drop is important because the higher pressure drop you have, the more fan speed you need, the more energy your HVAC system will use. So we want to decrease that as much as we can. As you can see, the lowest pressure drop was when these micro lines were orientated parallel with airflow. And the highest pressure drop was in this orientation where they're orientated perpendicular. That's because you can see here in that orientation, there's much more blockage of the ducts. And you can kind of see in here, there's like little distinct wood droplets in the 3D printed heat exchanger, blocking much less airflow than the aluminum heat exchanger, which is very blocked up. So you need a lot less fan power using this heat exchanger. And then conclusions, 2 manuscripts have been prepared from this work. There's one on the CFD models being submitted to the Journal of Applied Thermal Engineering, and the one on the 3D printed heat exchanger is going to be submitted to the International Journal of Heat and Advanced Transfer. Thank you. Thank you to Sam Lowry and the OERC.
Okay. Questions for Charlie? And if there's any questions online, just shout out because we can't see you. All right. We'll move on then. Thank you. Matthew?
Alrighty, hi everyone, my name is Matthew. I'm going to be talking about my project from last year, which over the summer consolidated the results from and got a manuscript ready for submission. So yeah, it's called a new method for testing heat exchanger water retention, which is what I was investigating. Right, so I'll start off with some highlights. As the name suggests, I developed a new method for testing the water retention of different heat exchangers. I tested 3 different surfaces, aluminium, which is commonly used for making heat exchangers, polylactic acid or PLA, which is the 3D printed polymer that we use, and then polydimethyl siloxane or PDMS, which is a hydrophobic polymer, which we can set to transfer a pattern onto it. We observed differences in water retention for each surface, which is pretty cool. And like I said, yeah, we were prepared in the manuscript. A little bit of background, which looks quite similar to what Charlie just talked about. So I'll just skim over it. But yeah, the key thing here for us is that HVAC systems all use heat exchangers, and they're quite a significant portion of global energy use and greenhouse gas emissions. So we want to make them as efficient as possible. Like Charlie said, in these we get condensation can occur. So we want to reduce that if possible. How do we do this? We take inspiration from natural surfaces like these ones. We have improved water shedding along the directions of these microstructures. So we want to put that onto a heat exchanger to improve the water removal. A little bit more background on why this happens. So different surfaces interact with water differently. We've got different levels of attraction, which we have ranging from hydrophilic to hydrophobic. So this is basically just a measure of how much water is attracted to the surface. So we get like really pronounced droplets on a super hydrophobic surface, but more like a film-wise sort of condensation on a super hydrophilic surface. And when we introduce structures like we find on a real surface, or the ones we use in this work, we can have these hybrid states where the water can collapse into the grooves between the structures or sort of sit on top. And for the surfaces tested in this work, we've got aluminium, which would fall in the hydrophilic regime, a coated aluminium, which is in the super hydrophobic. The PLA, 2 of them are in the hydrophilic and 1 in the hydrophobic. And in the PDMS, all of them in this hydrophobic regime. So quite a good range of surfaces to look at. A little bit more on the directional wetting, like Charlie was talking about. On a completely flat surface, like we have a control aluminium or a control flat PLA, we've got identical wetting in any direction. Whereas once we introduce these structures onto the surface, the profile of the droplet can change depending on the orientation. So this allows us to test different directions of the groove, so we can sort of see, right, does our test method actually show that we've got improved drainage with the grain, and if it's worse against the grain. So yeah, why do we need a new method? When we're testing heat exchangers, this is the traditional method that's sort of used. We take an entire heat exchanger network, like Charlie used in his work, quite a large piece of kit, hours and hours to create. We dunk that in a bath of water and then remove it from the water and measure the mass as a function of time. And it sort of produces something like this, which is nice and simple to look at. But there's a few problems with this because it's quite involved. We have to make an entire network of heat exchanger, which is time and resource intensive. When we're looking at our new surfaces, which are water repellent, it's quite hard to get complete uptake of water in each duct in the heat exchanger, so you don't get a full picture of what's happening. There's quite big problems with leakage in between each ducts just because we've got such a big system. And then more stuff with ring vibration, where we've got droplets coming out, maybe when it's bumped, stuff like that. So the aim, like I've got here, make a method which is repeatable, reliable, and can be done much quicker than this one. So this is quite a busy slide, but it's all important. The schematic here is what it looks like. As you can see, it's very similar to the traditional method, but it's a whole lot scaled down. So we're looking at just a single duct within a heat exchanger. And so what we can do with this, we've got improvements in the duct water level being visible, so we can see when we've got complete uptake. There's only one duct, so there's no leakage between them. And the way it's designed, we can test different surfaces in quick succession, which is exactly what we wanted. We can also test a different range of duct widths, which is good because in actual applications, we've got heat exchanger ducts, which will range from 1 millimeter all the way through to 6 millimeters. So testing a range of them is quite handy. With the new method as well, we've got the same sort of results on the left there, which is just our mass versus time for the water retention, sort of over a longer time period. And then we've also got what is called our rate of water removal sort of results. So we're looking at, do our surfaces that retain less water also remove them faster from the duct, which is another improvement on the traditional method. Yeah, so making the surfaces to put into our setup, we've got our 3D printers, which, as Charlie said before, we've got layers and layers and layers deposited, which builds up and creates a grain, which is the same sort of scale as our natural surfaces we've taken inspiration from. So if we stop there, we've got a cool 3D printed surface to test, but we can keep going and take that same surface and use it as a mold with our pattern transfer PDMS, which is pretty cool. It's just the inverse of our average 3D printed method. So the results we sort of have are twofold. We've got water retention results and then water removal results. And I've just got like an indicative comparison here. So between the control aluminium and the coated aluminium, we've got quite a clear difference in the number of ducts present, so the number of droplets present in the duct and the size of these droplets. The same sort of trend follows into the PLA and the PDMS, where the surfaces where we expect the droplets to be removed more easily have less droplets present at the end of the test. So yeah, that's just so we can see that without looking at all the numbers and such. If we go through into the actual results, we've got the water retention, which I haven't included all of them because it's very standard. We've got from the previous pictures we had less water retention than we expected it to be. So yeah, we saw from our wettability that we should expect coated aluminium to retain less water and to also remove it more quickly, which is what we see here at the 4 mil. It's probably where it's most pronounced, just because of the larger ducts, more bulk water movement. And we have similar trends between the flat PLA and the parallel PLA, like the directional wetting we talked about. And these similar trends follow through into the 2 millimeter results and the 1 millimeter results. So really quite a nice set of data, which is reinforcing what we expected at the start. There were more problems with the 1 millimeter results, just because as we get down to the smaller duct width, we have more influence from droplet bridging as we shrink that gap down, but still expected results in the 1 millimeter. Yeah, I'll just conclude by touching on what I said before. Tested 3 different surfaces at 3 different widths, and we saw differences in the rate of removal and the water each. And yeah, looking to publish soon in experimental thermal fluid science. Big thank you to Sam Larry for keeping me on over the summer, and to the OERC for helping him do that. Any questions?
Questions for Matthew?
Because you looked at the effect of orientation, but I didn't quite catch that. Like, I know it was on the slide, but I didn't really gather what is the effect of. Presumably, the parallel will drain faster.
Yeah.
Yeah.
Yes, yes, sorry, it's maybe not so obvious on my graph here, but we've got the parallel surface quite clearly a little bit faster, at least at the 4 mil, and then the perpendicular and flat are a bit similar, which is not exactly perfect, but that's a good indication of what we've got. And then the same at the 2 mil, yeah, that flat surface being the worst and the parallel one being the best. Is that?
Yeah.
Any questions online?
Looks like something in the chat. Oh, that was before. Yeah, it's good.
Yeah.
I hope it was.
Yes. Dirty can. No. All right. All right. Thank you, Matthew.
Thank you.
So I'm Brooke. I'm a third-year chemistry student. I'm doing work with Arjan in the physics department on the hydrothermal liquefaction of hops and hemp. So hydrothermal liquefaction is using high temperatures and pressures to try and break down some kind of feedstock. It uses water as a solvent and a catalyst, and we were operating in subcritical conditions. There are some studies doing supercritical, but we're trying to keep our costs down a little bit. And so you produce a char, an oil, and a liquid. And so we were more focused on the oil, which has been shown to have quite good energy recovery and can be used as a fuel in the future. And so we were looking at hops and hemp. And the focus was to try and change the conditions that we were using to maximize the yield while also still having quite a high quality oil. And I've got a little picture of the batch reactor that we were using. So the first feedstock I was looking at was spent hops, which is the remnants after the beer brewing process. It's quite like low value and it isn't really done anything with. And so this is following on from a previous student, Maya Gasson, who was looking at the effects of temperature. And so she was found that higher temperatures had better yields. So I then looked at the biomass loading, which was changing the amount of hops with water ratio. And I've got a little graph here. So the increasing the loading didn't really change the char a lot, but it did reduce the oil yields quite a lot, which kind of suggests that higher yields, higher loadings aren't really good for the yields, but there's a bit of a balance trying to maximize like the amount of material that you're putting in and trying to get a good yield as well. I did do some residence time runs, but unfortunately the heater we were using was quite unreliable, so a lot of the data wasn't very useful. The residence time was just changing how long the reactor was set at temperature for. And I've got a little graph showing how unreliable it was. So I've got the two, these were at the same conditions, but one of them took 3 hours to heat up and one of them took 4 hours to heat up, and they're quite different yields, as you can see. And then I've got another 20-minute one, which, so these had the same kind of heating rate, but they have quite similar yields. So it kind of shows that it's more dependent on the heating rate than on the residence time. The next feedstock that I looked at was hempseed cake, which is the remnants after hemp seed oil extraction, which again is kind of like the hops, where it doesn't have a lot of value. I'm trying to get an oil out of that, and I didn't have enough time to get a nice good data set for the temperature runs, but the first kind of trials that I did show quite good yields at around 20–25%, which compared to the hops is like about 9%, so it's quite a lot better. So yeah, there's kind of not enough data to really say a trend in the temperature, but so if this was going to be continued in the future, we kind of rerun the residence times with a better heater, hopefully, to see if we can get some better results for the hops, and then to continue the hemp trials to get a full data set on the temperature runs, and then also look at how the other conditions change. So looking at the biomass loadings and the residence times again for that. And I was hoping to do some analysis on the samples to get a bit of a feel for the quality of the oils, but there was some equipment failure and things kind of not really happening, where I wasn't able to run a lot of the analysis, but I think some of the TGA analysis is being run at the moment to try and see how the quality is sitting, to see what kind of potential source of fuel it could go towards. Yeah, so thank you. If you have any questions, I just want to say thank you to Arjun and to the OERC for helping me. Thank you.
Thanks, Brooke. Questions for Brooke? There's one online there.
The understanding of energy in and energy out. I wasn't really looking at, there was another student who was doing more of a modeling on the energy cost of, it was for diapers, but trying to have a look at what kind of energy it's going to use. Yeah, so I didn't have a lot of focus on it.
Is there another message there?
I think
okay.
that's it.
I don't think it's related explicitly to what you did, but do you have a sense of what material has greater potential in terms of total biomass availability? Like, are we hemp cake waste, is that on a similar scale in terms of volume to the brewing?
I didn't do a lot of the sourcing. The previous student of mine, I kind of looked at all the different feedstocks and suggested hops and hemp as potential things. So she would probably have a better understanding of, you know, the amount of availability.
Other questions? All right. Thank you very much. Maybe a round of applause for all of our speakers today. That was well done. And thank you to all of you online.